Hello everyone, welcome to my channel. Today we will talk about variational autoencoders. It is a technique that we use in data to compress high dimensional data to a much smaller dimensional data. A very cool application of variational autoencoders is in image compression. Let's say we have many images of people face and suppose that they have colors. The color can be separated into three channels: red, green, and blue. Now per channel, each image has 10,000 pixels, right? Because it's 100 times 100. And per pixel, we can represent that as a number between 0 and 255. So per channel is 10,000 numbers, and across three channels is 30,000 numbers. So per image, we can represent the image as a 30-dimensional vector. Now, the space that these images reside in is not that large because these images are not random, right? Because if the image contains people faces, the image or the pixel have to behave certain ways, right? Because we have the nose, we have the eyes, we have the lighting, and so on. These are very constrained, right? The pixels are not free. So these images live in a much smaller dimensional space. And we wish to know what is the dimension or the intrinsic dimension of these images. There are many ways to compress data down to a much smaller dimension, and autoencoders is one of those techniques. Here is the overview of variational autoencoders. Earlier, we said that we first embed our images into the ambient space R to the 30,000. This is extremely large. The manifold hypothesis say that our data manifold live inside a much smaller, smaller space. The reason is that the pixel are not free; they are heavily constrained. Now, what we do is that we embed each of those image into another space called the statistical manifold. Each point represents a density function. We actually won't be working inside here. We're going to work with a submanifold that contain certain Gaussians. These Gaussian, the variants are diagonal. Right? They're very, very simple. And in particular, we don't just embed them or send them to a random point in the statistical manifold. We embed them in such a way that they are very close to a particular distinguished point, and that distinguished point is this Gaussian. So we want these points to go to points that are very near this particular point, okay? And we want to do it in such a way where, right, we want them to be clustered around this distinguished point, but we also want to send them in such a way that we can always recover the original image, right? So they all cluster around a particular point, but they need to be distinctive enough so that we can always decode and get back our original image. So we have a mapping that goes from our images to the statistical manifold. Once it lands as a density function, we can use that to sample our Z, and that lands inside our lens space, RD, where D is much, much smaller than our original dimension of our ambient space. We need to map them here in such a way that we also have this decoder map that send our Z, which we view as a way to index the original image, right? We can go back and get our original image. We may not get the exact original, but we should get something extremely similar. Now, our decoder map should behave a certain way, right? Remember, we can view each of those sample z as a way to index our images, and then we have a map that sends those indices back to our images. Now, the decoder need to be smooth. What that means is that if we have two z that are very close, then we should get two images that are very similar, right? If two z are extremely close, then we should get two pictures that look like twins. Dense mean that no matter what z I choose here, I should get an image of someone's over here, right? So we can't just take a z and get some random image that doesn't make sense. Once we do our training, right, then we have a density over our latent space, and we call that Q. That density over this latent space needs to match up with this prior, right? And we'll talk more about this later on. The encoder, on the other hand, maps our image, our data point, to a Gaussian over Z, and not just any Gaussian. Um, the Gaussian where the variance matrix is diagonal. Basically, we're trying to keep things as simple as possible, right? So we have the encoder setting each point to each of this density function. And we want these guys to be as close as possible to our distinguished Gaussian point. And of course, we don't want all of them to go to a point where we can't differentiate them, right? So we want them to go to a location close to this distinguished point, but also they need to be in such a way where they can be unique, where the decoder can bring back and give our original image. Now, this is a statistical manifold. It has a particular metric on it called Fisher-Rao metric, and it's a Riemannian metric, right? No one works with Riemann metric. It's just intractable. A good thing is that that metric is locally up to a second order, the same as the KL divergence, right? Which is intractable, in particular in the case of Gaussian. Again, we're going to talk more about this later on. So we have our statistical manifold with coordinates mu and log of sigma. You may wonder why we use log instead of just straight up sigma. If you decide to use just sigma, then you have to keep the constraint that sigma is positive, because that's your standard deviation. But if you decide to keep the constraint, you have to keep the constraint throughout the gradient descent process. And the gradient descent process is going to push that to become negative eventually, sooner or later. So what we do is that, okay, say that this is just log of that, and then it can be allowed to be negative, right? And then to get sigma, you just raise it to the exponential. Now, we are inside our statistical manifold. We can't just use Euclidean metric because it wouldn't make sense. Because a small movement on a low variance axis is actually a large movement. But a small movement on a large variance is pretty much a small movement. So we need to use a metric that respects the geometry. So it turns out that the KL divergence does exactly that. And we're going to define what it is exactly, but for now we're just going to look at some of the properties. Now, the KL divergence is not quite metric, but it behaves almost like a metric, and it's a metric up to second order. And we're going to talk more about that in a bit. Now, so we're gonna fix a distribution, and we want to see what happens to the function as we move, away from that at a small increment. So it turned out that the KL divergence is zero exactly when the distribution is same. And that makes sense, right? We're going to define KL divergence as a way to measure the difference between distribution, and they equal to zero exactly when they're the same. Now, the KL divergence is non-negative and is zero exactly when these distributions are the same. So then that tells you by geometry that P eta is your minimum. So if that's your minimum, right, then the gradient of f at 0 is 0 because we have found our minimum. And of course, you can do some other algebraic manipulation to show that it's equal to 0. Now, the second order turned out it equal to something called the Fisher information, and it's our metric tensor. It provides the Riemannian metric that we need for our statistical manifold. So if you do from this information, and if you do Taylor expansion, then we get this, right? So because the zero order, the first order, they vanish, and then your second order is this, and then you just group all the third order up, into big O notation. So we see that the KL divergence is a metric locally, and is and this is called the Fisher-Rao metric, and this is the metric that we should be using for our statistical manifold. Now, of course, we don't want to work with this because it's intractable. So what we do is we work with the KL divergence. Let's look at autoencoder geometrically. So we have our data manifold, right? Each of this represents the image. We want to send each image to a Gaussian distribution, right? The red dashed line is what we want it to look like, and we want it to be pretty close, right? We don't want to send this to a bimodal Gaussian. We want it to be this normal distribution. So, we can send this there, or we can send this there, or we can send it to something that looks almost like a Gaussian distribution. Another viewpoint is what we do is we try to attach the statistical manifold one copy per data point. Okay, so what we want is a map that sends each data point to a point in S. Okay, so over up here in the total space, right, we have the distinguished point, the Gaussian distribution at 0 and the identity. So this is our constant section, and we want to send each image to a point in the distribution as close as possible to this constant section, right? So of course we don't want it to be, just like the constant section. Else, we cannot distinguish between these image point, right? Our goal is to make this point as close as possible to this red dashed line in such a way that we can still distinguish these image points. So recall that P of Z is the distribution that we want over the length space, right? And we're going to be using that to draw a sample and construct an image in the image space. But this right here is the distribution that we train on over C, okay? So if we want to draw from P of Z and we want to get an actual image, then these distributions should be extremely similar, right? So we need to train so that distribution need to match up with this distribution. I mean, they don't have to be exact, but they have to be similar, and that is measured by the KL divergence. So here you can see, visually what that means, right? We send each x to a Gaussian distribution, but overall, they should cover the same distribution as the prior P of Z because we want to sample from that in such a way that we get the an actual image in the image space. So here I do want to say that what we are trying to do works mainly for nice data manifold, in particular the data manifold consistent of images. But if the data manifold is more sophisticated, then we can't quite do the same thing here. You can't, create a map that preserve the topology from a sophisticated data manifold into something that's contractible. So here contract can mean that if you have any loops, it will contract to a point like RD that we're trying to map to, right? And on top of RD, we have our Gaussian distribution. So we could try to map it to an analyst, but it doesn't quite work because a Gaussian distribution, it has high density in the middle, but here we have an empty region. So if we take a random point z in the latent space and we try to decode it, we would get an image that doesn't really make sense. You could instead, okay, try to map it to something that looks like a Gaussian distribution, but it doesn't quite work as well, right? You could try to, cut it and map it to, some kind of diameter on here. But when you cut it, all the points near the cut, right, they are very close together. But in the image, they are very far apart, and that doesn't satisfy one condition for the, encoder and decoder. So we have to be very careful on the data that we try to use these techniques on. So we want to find a distribution that is as large as possible at our data point. Okay, such a distribution exists, but finding it isn't trackable, as you can see here. Right, there's no way we can, integrate this integral. Um, so before we move on, let's think about what this is. Right, this is the average over all the different ways that we could construct x from the lane space z, right, using the decoder, right? And we want this to be as large as possible over our images. But finding this thing is intractable. So what we do is that we introduce a different density function that is more intractable, the one that we can construct using machine learning, and that's q, right? So using the fact that log is concave, we can use Jensen inequality, and we have this nice equation here. This is the evidence lower bound. Now, the gap between the log of p of x and the evidence lower bound is the KL diversion between the posterior. Okay. Um, what we do is we want to maximize the elbow, right? By doing that, it will close the posterior gap. So here, remember that P is the ideal density function, and Q is the density function that we construct from scratch. And we want these two to be as similar as possible, right? Maximize this, but minimize this. There is a contention between two different forces that are inside the evidence lower bound. There's one force that tries to make sure that the each of the data point go to something distinctive so that we could reconstruct the points from the latent space. But there's also the KL divergence that want each x to go to a blob that looks like Gaussian. So there's one force that want to keep it distinct, and there's one force that want to keep it broad, right? So we want it to be broad enough to tile the link space, but distinct enough to encode X. Here is where we view the two forces as vector field. There's a vector field given by the KL term, right? It tried to push the distribution of each data point toward the distinguished point here, right? Basically, we want this section to be as flat as possible to the constant section. But over here, we have the reconstruction vector field that wants to make the points as distinctive as possible, right? So there's one vector force that collapses toward the P naught, and there is the reconstruction that wants to make the point to be as distinctive as possible so that we can construct it or reconstruct it easily. Now recall that we want to maximize log of p of x, and log of p of x is equivalent to the expected value of that particular function we saw earlier in the derivation of elbow, right? Um, so to maximize it, we have to find a gradient with respect to phi, right? Our encoder. But the problem is the act of sampling is not differentiable. So we can't take the gradient. So there is a clever trick where we push the stochasticity. I can never pronounce that word, right? So basically, make a z deterministic from phi, and then we add the noise to the standard deviation. Okay, so then we can bring the gradient inside, and now the gradient flow through the mean and the standard deviation. So there's something I said earlier that I wish to clarify a bit more. So the encoder send each image to a Gaussian blob, okay? Um, and that Gaussian blob can be of arbitrary size and at arbitrary center, okay? Here, the center is this the mu, and the size is dictated by sigma here. Now, these tiles need not to be equal, but they need to cover the prior Gaussian blob. Okay, so on average, these tiles need to cover the prior Gaussian blob, because remember, we want to use this guy as for image generation. Okay, so again, each data point or image go to a Gaussian blob, and on average, they should be equal to the prior, which is the Gaussian blob at 0 and their identity. Okay, now on the other hand, the decoder, okay, the decoder need to send each z to a Gaussian blob, okay, in such a way that it should cover the data manifold, right? So these Gaussian blob, they live inside the right, they live inside um, the ambient space, okay, and overall there should be no gap in the data manifold, okay. Now notice something that for tiles on the data manifold, we choose in such a way that the tiles are of equal size. The reason is that in the encoder, the KL divergence balance out or control the size of the Gaussian blob. But for the decoder, there's nothing that can balance out that Gaussian blob. So if we use if we allow this size of the tile to be arbitrary, then the size could go arbitrary to 0. Okay. Now let's take a quick look at a single step gradient descent. What we do is we take a mini batch of independent draw, right? So per batch, you have b number of images. Now, each image or each data point, right? We it goes to a Gaussian blob, okay? And we want to find out, okay, what is the expected value of this, right, over the entire Gaussian blob? Remember, this is our reconstruction term. We want to, we want to maximize this. Okay, so we're supposed to integrate the log over the entire Gaussian blob, and that is intractable. So in general, we would have to use the Monte Carlo technique. We would sample many times and then take the average. But instead of doing that, what we do is we, uh, take one single sample z, and that will be our uh, um, approximation to this expected value, right? So the expected value of this is just plugging in a single sample from the Gaussian blob. So, of course, this will be a noisy estimate, but it has very low variance because we control, right? Remember, z was constructed deterministically from phi, and we push um, the randomness, right, through epsilon, right? So this epsilon, remember, was we multiplied that to our variance, right? So per image or data point, this is our approximation, and then we do the same thing to every single images that we have chosen in the batch. We approximate, and that will help us determine the step size. Now, as you go to this, right? As you go to per step, each data point will be chosen multiple times, right? And each time a different z is chosen. Okay. Um, Now, furthermore, the only thing that we approximate along the way was this guy here, while the KL divergent has a closed form. Okay. So overall, it's not a it's not a bad approximation, but it's actually a very good approximation. Let's take a quick look at the encoder architecture. So the encoder purpose is to take a data point and send that to a Gaussian blob. Okay. So per data point, right? It depends on what kind of data you have. If it's just tabular data, then you can use some kind of MLP. But if it's images, then you have to use maybe convoluted neural network. So, and then from there, right, you use a learn matrix for each, right, and some bias vector to construct the mean and the variance. Now, this is not quite the variance, right? This is the log of the variance. Recall that the reason that we use log so that we can, we don't have to clip it, right? Because this allows us to take a negative value, and to get the variance, right, you just raise it to the exponential. All right. Now, this gives us our Gaussian blob, right? So remember, from the one Gaussian blob, we pick a sample. And how do we pick a sample? Just take the mean and then add the the variance, and then you multiply that to by that randomness. Okay. All right. So that's the quick look at the encoder architecture. Now we look at the architecture of the decoder. Remember that the decoder take a z from our latent space and send that to a Gaussian blob in the ambient space. Okay, and these Gaussian blob they should cover our data manifold. Now here the trunk should mirror that of the encoder. Mirror mean that it's the same architecture but just going backward. Think of it as like an hourglass, right? The hourglass for the encoder will go from large dimensional space all the way down to a much smaller dimensional space, and then the decoder does it backward. You go from the smaller dimensional space to the space that contain our data. Okay, it depends on what kind of data you work. So here we're just going to stick with continuous data. So right, this z would map us to a Gaussian blob because the variance is fixed. We just all we extract from it is the mean. Okay, so then we from that we have an approximation for the log of the likelihood. Again, because we assume that these are Gaussian, so we use the formula for the Gaussian density. So this gives us an approximation for the reconstruction error. Okay, let's see what the forward pass look like. Right, we start with our data point, we encode it, so that gives us a Gaussian blob, and then from the Gaussian blob we sample a single z. Right, to sample we just pick a random noise from the another Gaussian blob here, and then we have a particular sample, a low bias, could be noisy, but is the bias low. Okay, and then the decoder go backward, right? It take the z and then send us back the data point. Now, then we want to know, okay, how close is the original data point compared to what we have here, right? So in the next stage, we're going to talk about uh, the the training loss. From earlier, we start with our original data point, and then we construct an approximation for that, right? So the X go through something that looks like an hourglass, right? The encoder shrink it, and then the decoder try to reconstruct that, right? So remember that the loss has two parts, right? There's the reconstruction loss, and there is the KL divergence loss, right? One good thing about assuming that everything is Gaussian is that the KL divergence has a closed form, right? That's really nice. So the only thing that really require approximation is the reconstruction loss, right? So that is the one where we use very basic Monte Carlo. All right. So we have so the whole entire loss consists of two parts: the reconstruction and the KL divergence, and both part are differentiable. Then we can just do our normal gradient descent, and then take the required step. So let's look at the overall architecture of the training. Right, we have our data point. The encoder send that to a Gaussian blob, and from the Gaussian blob, we choose a single z, right, to estimate the reconstruction loss. And then the decoder try to reconstruct that to give us our x hat. And once we have our x hat, then we calculate our loss. Remember, we want to maximize the elbow, right? But then instead of maximizing the elbow, we just minimize its negative, right? Because in machine learning, we always try to minimize instead of maximize. So once we have something that we want to maximize, we take a negative and then we minimize that. All right, so we go to the training, and then we have our model, our autoencoder. And then one cool thing, right? So it does many things, right? Help us decompress the encoder, right? Decompress our data, but the decoder help us, with image generation. So if I pick any z in this prior, right, plug into our decoder, then we get an image. Furthermore, right, you can create image that never existed in your uh, in your tra- um, in your training data, right? So if your training data consists of 1,000 faces of people, right? Now the decoder can construct a brand new face that wasn't in the training data, and that face would still make sense. Okay, which is pretty darn cool. Let's look at this summary geometrically. So we have our data manifold, right? There is a map. In the language of our bundle, we call that a section. It's because if you draw it out, you actually see a section of um, the product space. Now, all right, so you have a map that goes from the data manifold into the statistical manifold, and where we want to map these Gaussian blob to a distinguished Gaussian blob, okay? Because we want to keep things simple, and it's easy for us to do image generation, okay? So in this space, there's an actual metric called the Fisher-Rao metric, but that is a Riemannian metric, which is intractable to work with. Um, we could, what we do is we use the KL divergence, and that is a local metric, and it's equal to the Fisher-Rao up to a quadratic form. Excuse me, a quadratic term. Okay. All right. So you send to these point. Okay. So the KL diversion make these point as close as possible to this distinguished point. But there's another term, the reconstruction term. Make sure that these Gaussian blob are distinctive enough so that you can always go back and reconstruct your original images or original data point. All right, so let's see here. So here's the what's happening overall, right? So here we have our data manifold, and on the y-axis we have our statistical manifold, right? So per data point, above it is the entire statistical manifold, and then per data point, right, what the section does is that it would try to choose a point in the statistical manifold, right? So per data point, we choose a point in the statistical manifold, and that's what we're doing here. So originally, right, we just kind of send them randomly before training, right? So they are pretty far from the constant section. we want them to be as close as possible to the constant section, right? The constant section where you map everything to the distinguished point. But we want them to be close. We push, the training will push these points down. But remember, we don't want to be all of them to be the same because we want them to be distinct so that we can always go back to our data point. And look, right, they're pretty close and they are all pretty distinct. So with the KO divergence between, these points and the constant section is pretty small, and they are distinctive enough that we can always go back to our original data point. All right, and this concludes this video. Thank you for joining me in this lecture. I hope you have learned something. Thank you.